So the adjacency matrix, it presents the heart of the graph. So here we will discover different properties of the adjacency matrix and also try to kind of diagnose it. So when does it become kind of, less resilient to attacks? How can we diagnose the adjacency matrix? How can we know and extract the properties of an adjacency matrix? And let's start with the first simple property, which is, as I mentioned earlier in the first part. So we had directed, undirected graphs, weighted, and binary graphs. And here we'll see that an undirected graph is actually has a symmetric matrix. So for example, in this case, let's look at this, adjacency matrix A. So this is our adjacency matrix. And we have two pairs of nodes. So this is, node, call it I, connected to J. And here, J to I, right? So these two elements are actually symmetric. And you can see that when we have Aij equals a, Ji, it means that our matrix is symmetric, which means these two weights are the same, which implies that we have only a single edge here. So we have an undirected graph. And the value inside, so we're going to put a value inside. So let's put, for example, I don't know, like 0.1. So we have a 0.1 right here. Okay, so on the other hand, we can also have what we call asymmetric matrix. So asymmetric matrix, so these are the block diagonal, or the diagonal elements. So the diagonal elements, all these, if we have self-connectivity, so let me just remove this. So if we have self-connectivity, which means the node is connected to itself, it will be 1. It will be, for example, 1. If we don't have self-connectivity, we don't consider these edges, so it will be 0. Okay, so it depends on whether we consider self-connectivity or not, whether we have a simple graph and not a single graph, but that's just a note on the side. Now let's go back to our original problem, which is, is this matrix symmetric or not? So in this case, the matrix is not symmetric. Okay, so Aij is different from Aji. So if we take these two elements right here, so the first element, we can have 0.1, and the second 0. For example, 3. And you can see that from this is I, J. So from I to J, so if we put this is I and this is J, so the value here is actually 0.1. So it's this value. And then from J to I, the other way around, we have a thicker connection, which is of strength or connectivity weight, 0.3. Okay, so this graph is directed. So in this case, we have a directed graph. So whenever we have a matrix that is asymmetric, it means our graph is directed. And when our matrix is actually symmetric, it means our graph is undirected. And now let's look at how this manifests the problem. The second layer, or the second question, is our matrix weighted or binary? Is our graph weighted or binary? So when we have, for example, a bunch of zeros and ones, so which means if two nodes are connected, we're going to put 1. So the weight is always set to 1 whenever they are connected. And if they're not connected, for example, here we can add another node. And you can see that these two are not connected, the pink and the white. So if we're going to add the white here, it will be 0 over there. Okay, so because they are not connected. And so this is basically how we define binary matrices. So binary matrices have only 0 and 1. And of course, the matrix is symmetric when the graph is undirected, and asymmetric. So here, actually, when you have, so that's another question. So let me ask you, can we have, for example, a binary matrix that is asymmetric? So I want to think about that in a bit. So that's a very important question here. So here, you can have a sense of directionality. So you can have a binary matrix and say, my matrix is binary. I only have 0 and 1s. So in this case, you can see it's undirected, okay? But we can add directionality for sure. That's not a problem, okay? So this is also a generic case. So you can have, for example, I and J. So if you say I and J connects in this direction, so you're going to have 1 here. And then when you put the J over here and the I, the connection between them, the opposite direction, is missing. So that's a 0. Okay, so here you can have binary symmetric and asymmetric matrices, and you can have the same, of course, when you have a weighted matrix. It's a more generic. It's a generalization of the binary. So this is a weighted matrix, and this is a binary. So in a weighted matrix, Aij can take any value. Okay, so here, for example, we can put -5.1. And here we'll have our connection. If it's undirected, -5.1, and here it should be symmetric, -5.1, if you put the same elements over there. Okay, so so these two are symmetric with respect to the diagonal of the matrix. All right, so now we have seen the first type. Now let's move to the second, the second property here. So basically, this is actually there are two things I want to present here. The first thing is the scale or the size of the graph, the concept of density and sparsity. And the second concept is permutation and variance, which is a very important property of a graph. So the scale or the size of a graph is encoded in its matrix. So when we have a matrix, an adjacency matrix like this, okay, so there are two things here. There is the number of nodes, which we can denote also as V, the cardinality of V. And there is what we call the number of edges, and we can count. It's the non-zero elements in A. And, if we call this E, so it's basically the size of E. So, so in this case, the A defines what we call the scale of the graph. So the scale of the graph is encoded or is represented by the number of nodes. The more nodes, the larger the graph, the more edges, the denser the graph. We can also, look at how many edges we have. So if we have, for example, if 90% of the edges of E is 0, then we call this a sparse matrix, more than 90%. So more than 90%, the other way around, more than 90% is actually, it means that we have lots of zeros in our matrix. So our matrix becomes sparse, which means we have sparsity, we have lots of zeros inside the matrix. That's what it means. So when the matrix, on the other hand, we have, loads of connections. We have, for example, many dense connections in A. So it means that here our matrix is dense. So we have, so this is, just in a very naive way. So this is how we define this. So one is sparse and one is dense. So the next one is basically when we have, as I mentioned, when we have non-zero elements, this gives us the number of edges in A. Okay, so there are two elements here. When we look at scale, nodes, okay, so the node size and the edge size. All right. All right, so basically the sparsity and the density are very important properties of a graph because if we want to examine the connectedness of a graph or the diffusion of information along the graph, it's important to kind of quantify the number of edges, connections, and also examine the number of nodes that we have in the graph, okay? So as these numbers increase, it means that we have huge graphs. We can have graphs with billions of nodes and edges, and computations on those graphs becomes very challenging, and we will see that towards also the end of this series. So now we will look at an important property of graphs, which is what we call permutation invariance. Okay, so permutation invariance, it means when you have nodes. So let's say, for example, I'm going to draw an example, a simple example here for you guys to understand. So let's start the story with this kind of simple graph. So we're going to start with node 1, 2, and 3. Okay, so it's a V graph. So maybe I should do it in the other way. So let me just do a V graph. So we have 3 nodes here, and let's duplicate these 3. Okay, and we're going to create an adjacency matrix of 3 by 3. Okay, so it's a 3 by 3 matrix. And in this case, in this matrix, okay, so we have 1, 2, 3, 1, 2, 3, 1, 2, 3, okay. And then here, we'll see that, let's fill this matrix first. So this matrix of this graph, so we don't care about the diagonal. So we're gonna look at 1, 2, so 1 is connected to 3, so we have 0, 1, and here it's should be symmetric, so we have 0, 1 over there, and then 2 is connected to 3. So that's our adjacency matrix. Now we're going to change the ID or the indices of the nodes. So we're going to put 3, 2, and 1. And this is, 3, 2, 1. So basically I changed the ID of the nodes, and I'm going to put here, or maybe I will permute them completely. So I'll keep them the same, but I will permute them in a row. So I'm going to do some permutation or switch them. So here, let's do 1, 2, 3, but I'm permuting here. So you can, guys, you see that I can change the indices here, or I can change them there. So there are different ways. So I can keep, 1, 2, 3 here and scramble or switch the rows here. So permute basically the rows. So I'm permuting 2 with 1 and keeping 3. So this is, one possible permutation that I can do to my matrix. And what happens when I do that, so if I do this permutation here of the indices of the rows and the columns, okay, so I permuted 2 with 1, I switched them. So let's look at the topology of the graph. So 2 here, 2 is connected to 3, so we have 0, 0, 1, okay, and we have here 3 is connected to 1, 1, 1. So in this case, we have the same kind of matrix right here, but we can do it also differently. So we can, like switch basically the number, because we have symmetry in this graph. So that was kind of lucky, but you can try different examples. The matrix can change if we change basically the connectivity there. So if we have complex graph and we change the type, we permute the indices. So we use something completely different. So 3, 2, 1, and I'm going to do 1, 2, 3 like this, 1, 2, 3. So in this case, 1 is connected to 2 and 3. So 1 is connected to 2 and 3. So 1, 1, and here 1, 1, and 2 and 3, they're not connected, 0, 0. So what happens here? You see that we have a different connectivity matrix, okay? So especially in these highlighted elements right here, because we did this kind of permutation. All right, now, so we have a symmetry in the graph. That's why the first example was very unique. We got the same matrix, but this is a better example. So here you can see that we had a different adjacency matrix. Although the adjacency matrix is not the same and has been permuted, right? Is the graph remains the same, okay? So these two adjacency matrices, they encode the same graph. So both of them are correct, okay? So that's why we say that graphs are permutation invariant. So graphs are permutation invariant because every time we change the indices, we randomly assign these numbers and we get a different matrix. We may get a different adjacency matrix, but we will get the same graph. So which means these two matrices right here, they encode exactly the same topology. the same topology, okay? So here in this example, this is called permutation. So how do you permute a matrix? So it's very simple. So you take a matrix X, and here, if you want to permute, so for example, for every single row here, if you want to permute, for example, node I and J, in this matrix P, you need to put 1 here, and the rest, you set it to 0, okay? So that's called a permutation. So this is a permutation matrix. And this permutation matrix, it's a matrix where exactly 1 entry in each row and column take the value 1, and the remaining are set to 0, okay? Which means in each column, each row, you're allowed to put only 1. So that's a permutation matrix, which means you're permuting or you're switching, okay? Node I with node J after the permutation. So here, all of these guys should be also 0 because you're setting only the element ij to 1 in this case, okay? So here, we map from one indexing to another. So through this multiplication, we change the indexing of nodes. So what it means, after this multiplication, you get xi. You guys can play with it, by the way. I strongly recommend that you take pen and paper, and you draw a small symmetric undirected matrix, and you create your P, and you try to flip your graph. So for example, if we have a graph like this, so this is our graph, original graph, okay? And let's say this is my I, and this is my J. So when I multiply by P, this P, imagine that everybody is 0. Everybody else is 0. So when I do the flipping here, it means I'm permuting only, I'm switching only I with J. So after the permutation, I'm going to get X prime. And in X prime, I will have the new connectivity. Of course, patterns need to change. Things need to change around. But we're getting basically, we're flipping, this J will be here and J will be here and I will be there. So we need to kind of predefine the structure based on the topology or the connectedness that we had before. Okay, so after this permutation, you will see that X prime will maintain the same topology. So we have same topology as X, but we have permuted or kind of, 2 rows here, which are R and J. All right, so we're kind of did a permutation of these connectivities in rows, and also we need to think about the columns I and J. All right, so you can also think about this, we can have, if you have a matrix with different dimensions, so if your matrix is not necessarily symmetric, you can always, map and map back. So here, this is getting to get another, a matrix A prime. So this matrix A prime basically allows us to go from the permuted version and then to permute back. So we should get actually a similar matrix here. So this is P transpose. We're transposing the permutation matrix. So we're applying it here. We're indexing and re-indexing back again. So with this permutation, we should get an A prime, and this allows us to kind of restore the matrix, okay? So now let's move next. So next we have a very interesting concept, which is the power of integration. So far we have seen 2 points. So we have seen connectivity, symmetry, weighted and binary matrices, the importance of the scale and the size of the matrix, nodes and available or existing edges, permutation and variance of the graph, which is very different from spatial images, because if you're working on images, you cannot do permutation of, you cannot flip or permute these 2 pixels and still get the same image. So if you apply a permutation here, you're going to have a puzzle, right? So you cannot apply this to what we call spatial images. Permutations do not apply to images, but they do apply to graphs, which is really nice property to have. And now we will look at the power of matrices. So the power particularly of linear algebra and matrix multiplication by a vector. So by multiplying a matrix, so let's say here, this is our adjacency matrix. We will, multiply it by V. And after we multiply it by V, we will get an output vector. Let's call it, for example, here, well, for the sake of simplicity, let's call it Y. And what happens in here is that, so I wanted to focus on the top part. We have our n by n matrix. We multiply it by n by 1 vector, and we get an n by 1 output. So every time you do a multiplication, we are leveraging what we call the aggregation power of a matrix. So this multiplication right here, which is by the adjacency matrix, it allows to aggregate and integrate information along each node and its local neighborhood. Okay, so let me explain that. So every time you take a node, okay, so let's say this is node I. Okay, so this is my node I, and let's say this node I is connected to only, for example, 4 nodes. All right, so it's connected to only 4 nodes. Let's say these are the nodes and the rest are zeros. And what we do when we do this multiplication, I have a vector, I have an input vector here. So this input vector will basically gets multiplied by this, the horizontal row right here. And what happens is that I'm going to only keep, it's a weighted sum, I'm going to only keep the values here. So if the rest are zeros, right? So we have 0, 0, and a bunch of zeros. So 0, and then a 0, we have, I'm going to put 1, 1. So just a bunch of zeros and 1. So let's replicate that. So when you do the multiplication, right? So all these values right here will become 0. So we don't care. We will completely remove these values and do a weighted sum. So the way to think about this is that every time you take an element and you multiply it, by the edge connectivity weight of this node I, somehow I'm calculating a weighted local averaging of V by n of I, which is the neighborhood of I, which is very powerful. So think about it. I'm looking at my vector, all these values, and I'm calculating a, I'm trying to get the value here, yi, the output yi. So this element is calculated as a weighted multiplication, element-wise multiplication and summation of each of these elements in V and each of these elements in my adjacency matrix. So somehow I am integrating information along the neighborhood by taking this V vector as a weighted vector. Okay, so it's actually a very nice thing to do, which means, every time I'm looking at V, I'm looking at with the lenses, I'm calculating or computing the diffusion of V. So diffuse V across, A, I, okay, which is row I, and then here we have all other elements, J. So we vary the J number of columns, and through this diffusion process, I'm going to get a value here. So this is my output, and I do that again and again and again. So for example, for another node here, let's call it node K. So node K maybe has only 2 neighboring nodes, so 1, 1, and the rest 0. So what's going to happen is that I'm going to multiply this vector by, the neighborhood of K, and this will filter out all the remaining values. So everybody here will get nullified. It will be assigned 0, and I'll only care about these 2 values. So I take these 2 values, for example, 0, 5 and 0, 3. And here, let's say we have 2 and 6. So I do, 2 times 0, 5 plus, 6 times 0, 3. Okay, so this is, the first and the second connection. So let's call it 1, 2. So 1, 2, right? So this is the value that we're going to get where at the output. So what did we do here? We did an integration. an information, a weighted information integration for this element here, K, and along this vector. So it's kind of, this multiplication is very, very powerful, and you'll see later how we will leverage it in GCNs and graph convolutional networks, and learning how to embed graphs and nodes, how to represent graphs, how to do diffusion on graphs, how to find the shortest pathways, how to also do supervised and unsupervised machine learning tasks. And I'm going to draw an analogy here. It's a beautiful analogy. In this analogy, I would like you to look at the bottom part. So what we have here is actually a very typical problem. So we have a matrix. So this is our A matrix. Okay, so this is our matrix. And then we multiply the matrix by the vector. So we have a sort of an integration, an information integration along the topology of this matrix. So the elements, all these, the rows of this matrix, of this input, vector, right? And then we're going to get an output, and how we formalize all machine learning tasks. We have seen in the deep learning series that all machine learning tasks can be formalized as a matrix factorization. And this is, for example, a simple a simple regression model. So what we have, basically, we have our matrix X, and when we multiply X by a learned weight, so the green vector becomes the weights that we want to learn. So this is what we want to optimize. Let's say to optimize, okay? So we want to estimate this W. The X is the input data that we have. So that's, our input. It could be the input graph. Here it's the input training data. So we have N samples. Each sample is represented by D features, okay? And by mapping the samples via the learned weight, so each one at a time, through this projection or this mapping, this also we call it the integration step that we have through this multiplication, we're going to get the Y tilde. And the Y tilde is actually the predicted scores. So if we're doing prediction, so these are the predicted scores in this regression problem. And what we want to have is we want to have these predicted scores very close to the ground truth one, which is the ground truth vector. So in this case, we have N training samples. We want to predict all their values. And you guys can see that these two are very similar. So what we're doing is that in machine learning, we try to learn this mapping W. And if we learn it very well, we can predict almost the same values here. So if we have a class, for example, 1 here, we can get a very close value, 0.8. And this 0.8 will be very close to the class 1. So which means we predicted the label of this sample correctly here, okay? So this is basically also matrix multiplication. And you can see that in this case, I summarized it using this computation, this simple graph. And in this simple graph, what do we guys see? So we see that first we have all the weights. So also we can model this graphically. So this can be modeled graphically. So here we have our weights. Okay, so we do the summation and we multiply them by the input. So this is for every single input. So let's say all inputs here have 1. So the first value is 1. So we have seen before that this is for actually the bias. So if you guys haven't seen this before, you can watch the deep learning series, or the machine learning also and any introduction to machine learning and linear regression course. So we need to have the biases. But what I want you to keep in mind that this vector is actually this one. Okay, it's exactly this one. And by multiplying this vector by the weight, so we're taking this vector, we're multiplying it by the weight. This is what happens here. And then we're multiplying and summing. So this is the vector matrix multiplication, right? And then we're going to get exactly this element that I was talking about earlier, the yi. So this is our element right here. And it is the predicted output of the score that we want to predict. So here, this is what we want to kind of predict. If we learn a good W, our output yi hat will be very close to yi, which is the ground truth output value. Okay, So yeah, so this is basically this summarizes everything, and it's very important to understand the power of integration and multiplication, matrix multiplication by vectors or by matrices or tensors by tensors, because it's all about, you can look at it as a diffusion process, as an integration process, as a mapping or projection process, through a learnable basis here, a learnable weight W. So all these words are the same. So diffusion, integration, projection of A onto, for example, here we called it V, or X projection, mapping also. So all of these are, they define the same phenomenon, okay? So the next, or the fourth property is a very important property. So it's topology. So the adjacency matrix encodes the topology of the graph. And here there is a full lecture 2 of the graph theory series. So I strongly recommend that you guys watch it if you're not familiar with centrality measures and such as between the centrality, degree centrality, strength, page rank, eigenvector centrality. So I cover all of these in detail in this lecture. But today I just want to give you an overview of the importance of topology. Why is it important? How we actually define it? What is topological about the adjacency matrix? So here we have actually different measures that we can define to identify or quantify the topological importance of a node. So this is a function that quantifies, okay, or measures the topological role of a node n. And on the other hand, we have also a Fe. So Fe here is a function that allows us to quantify the topological role of an edge E. Okay, the input is our matrix, and we have lots of we have many centralities and measures that we can use. For example, here degree centrality. So degree centrality is very simple. So we use it for binary graphs. So you sum the number of connections that we have for. So here, if we note I, so for each, for j in the neighborhood of I, you sum their weights. So Wij. So here you can see this is the strength of node, basically I, okay? Or the degree, let's call it degree, because degree, we use it for binary graphs, strength for weighted graphs. So di, in this case, di is equal to 3. So it's very simple, actually. So that's the degree centrality. So you can see, for example, in star-like graphs, so this is a star-like graph. The central graph is the most important graph right here. So this is the most the central node that is highly connected in this graph. So all of these nodes have a degree of 1, except of this one has 1, 2, 3, 4, 5, 6, 7, 8. So it has a degree of 8, this node. Okay, cool. So now for the edges, the same thing. So let's say you have, a graph that looks like this. Okay. And you can see that all the other edges, all edges are kind of, we have a different distribution of edges if we want to identify the most important edge. So what is the most important edge here? So if you look at the whole topology, if you look at the topology of this graph at the patterns of the pathways, you will notice that this is the most important edge, because if I remove this edge, I disconnect, I fragment the two clusters or the two modules of the graph, okay? So this edge has the highest flow of information. So to go from A to B, I need to traverse this. To go from any node in, module 1, M1 to module 2, I must traverse or go through or pass through this edge, okay? So to visit any node. So this is why this edge is a central edge. And you can use, for example, measures such as betweenness centrality for edges to calculate or to get a number, actually, to get a value that tells you that this has the highest, for example, betweenness centrality, and the rest are, you know, quite small. So these values are very small. So once you do that, you can somehow read the topology. You can read the topology of a graph somehow, not read, I wouldn't say the word read, like you'll kind of eavesdrop, okay? Eavesdrop on the topology of a graph by plotting what we call the topological measure distribution. So it's a distribution that we are plotting here. And this distribution, it tells you that, for example, here there are very few nodes. So in this distribution, so we have the frequency, how many nodes have this value, this topological measure. So if you look, or how many edges, if it's a, you know, if we are plotting the topological distribution of edges, okay? So here we see that we have low frequency, which means very few nodes have very, they do have very high centrality measure because we are in this spectrum, so very high. And in this graph, we see that a few nodes here, so not few, sorry, many nodes. So we have a high number of nodes having a sort of a medium or low kind of centrality, okay? Or topological measure. So centrality is one of the topological measures, just, you know, this is an example, of course. But what this tells us, it tells us that, well, I have a few hub nodes here that are highly connected, and the majority of nodes are equally connected. And you can imagine the structure of the graph from this plot. So for example, here, if I plot the edge centrality distribution of this graph, so I want you to imagine that, guys, with me. So here we have the frequency, and you can see that for 0.7, so 0.1 and 0.2, so you have a lot of edges that have this kind of these values, right? So you have a peak here, but for 0.7, you have only one edge. So this edge turns out, so it's only one edge, which is this one, the central edge. This is the outlier. This is the most important edge that we don't want to break. So somehow this distribution tells me a lot about the potential structure of the graph, okay? So in terms of topology, we looked at two things here. We looked at the nodes and the edges, but this is a very reductionist definition of topology. Actually, this is what we call the micro scale topology. So when you look at the micro scale topology, you look at both edge and node centrality measures, okay? But when you go, you know, when you increase the scale, we go to the mesoscale. Now we look at the organization of the graph. So this looks at the organization of different structures in the graph. So we find, for example, a core and periphery structure. So we will see this in a bit. We also, if we go also scale a little bit more, so we discover, or we the macro scale, okay? So at this scale, we look at the big components in the graph. So it's not just the meso or medium structures, that, like, you know, the global structure of the graph. So you can see that there are different measures and different techniques and methodologies to read and understand or pin down the topology of a graph at a micro, meso, and macro scales. Okay, cool. So next, I'd like to cover in 5 the walks or the powers of matrices. So this is actually a very powerful you know, part or property, I would say, of the adjacency matrix. So far we have seen that matrices have the power of integrating information. We have seen that matrices have also, they tell us a lot about the topology. So if we feed the matrix into a function that measures or quantifies topological measures, we can derive distributions. And based on those distributions, we can understand the structure of the graph. And now we look at the power of matrices. So when you raise, for example, this matrix to the power of L, so raising this matrix to the power of L, what does it tell us about, you know, the graph itself, or edges and nodes in the graph? Okay, so let's start with A here. So in A, we have an example graph. So this is a simple graph. And then in B, this represents the adjacency matrix A that contains the number of walks of length 1 from node M to node N, okay? So this A is actually, it's our adjacency matrix. This is the regular, so let me use a different color. So this is our regular adjacency matrix, okay? Adjacency matrix. So this is what we had before. So if you look at this graph, so you encode it directly into this matrix, it means we're only measuring or recording in this matrix the connectivity between, for example, node 1 and 2 are connected, so these edges, right? And this is what we call a walk, okay, of length 1. Okay, so you walk from one node to the next node, and the length, to a target node. So you walk from a source node to a target node, and the length of the walk is 1 here. So this is considered as a trivial matrix. So because it contains what we call the number of walks or edges here of length 1 from pairs between pairs of nodes. So now let's look at the third case. So here's C. So when we raise A to the power of 2, so we raise A to the power of 2, you take just, you do A times A, right? So that's A squared, and you get this matrix. So you just calculate this matrix. And when you calculate this matrix, we have a beautiful property here, and you guys can verify it. So I also gave a full lecture on this. In the graph theory series, but here I'm just covering the basic concept so you remember how we define or identify or find walks between pairs of nodes using the power of matrices. So here in C, we have the squared adjacency matrix, so let me just use this smaller, okay? So which contains the number of walks of length 2 from node M to node N. So from one node to another. So for example, if you take, let's say, any, so we have 1, 2, 3, 4, 5. So you take, for example, node 5, okay? And then you take a node 1, which is 1. So here 5. You will see that you have, the length of the walk between 1 and 5, or from 1 to 5, is actually of 2. So you always need to have kind of, that's the least, the minimum number that you're having here, which is 2. Okay, so that's the shortest distance. So you can get to 5 by a walk of 2. Get to node 5 from 1. Of course, you can make your path longer, right? You can say, oh, I can actually walk longer, like, and get to 5 from this path, but that's not the point. The point here is like we want the shortest walk, okay? So you can see that amazingly, this matrix power tells us that, well, the walk between the shortest walk between 1 and 5 is of length 2. And you can see that also, you can verify that for other nodes and different pairs of nodes, okay? So now in D, so we have here, let's move to D. So in D, we have, when we pre-multiply this vector by A, the result contains the number of walks of length 1 from node 6 to each node, okay? We can reach nodes 5, 7, and 8 in one move. So basically, when you multiply this vector by A, okay, so this gives us the number of nodes. This gives us the connectivity of node 6. So we're looking at 6. So here we are interested in node 6, and we're multiplying it by A. So A here, it means we're interested in walks of length 1. Okay, so this multiplication will give us the number of walks that basically it contains the number of walks of length 1 from node 6, starting from node 6 to each node. So we can reach, for example, nodes 5, 7, and 8 in one move. So these are the 3 nodes that we can reach. So from 6, we can reach 5, 8, and 7 with one hop, or one jump here. Okay, so now when we multiply, so on the other hand, so let's look at the matrix power. So when we multiply, pre-multiply the same vector, this vector, okay, by a squared, the resulting vector contains the number of walks of length 2 from node 6 to each node. We can reach nodes, for example, here, so if we need 2, so we can reach 3, 5, 4, and 8. Okay, so it gives us basically all these nodes, and it returns the list of nodes that are 2 hops away. So this multiplication returns a list of nodes that are 2 hops or 2 walks away from the anchor node. Okay, so the anchor node is node 6 here, and this is really fantastic. So I want you guys to take some time and try to calculate this on take pen and paper and try to play with this. It's a very powerful concept because now you can explore neighbors and neighbors of neighbors by raising a to the power of L. So here, for example, we can find walks that have L length, right? So there are we have L basically hops to get from one particular node to another node, and we can identify these nodes. We can find them out by raising a to the power of L. Okay, as we did here for this particular example. Now let's move to the next point. So the next point, so before we wrap up, so we have 3 more to cover. So number 6 is actually here. We're going to look at the spectra of a matrix. Okay, so the eigen vector or the eigen decomposition of a matrix. This is a very powerful concept that permeates machine learning, where we define data covariance matrices, and also graph learning or graph-based learning, where we decompose, we do the eigen decomposition of the adjacency matrix of a graph. So let's start first with the definition of, the simple definition of an eigen decomposition. So here we have an A matrix. Our A is an n by n matrix. It describes a system that affects, some linear geometric transformation of a vector, right? So the linear transformation of a vector, so we want to kind of, affect the x through this multiplication. So I mentioned earlier the power of diffusion, integration. So A is affecting basically this vector. So this is another reading. So A is, applying a linear geometric transformation of this vector. So now we are talking about mathematical geometric transformation. So this is another power of this, or another reading of this multiplication, matrix and vector multiplication. So if we decompose this, so AX is, when we do the eigen decomposition, we want to rewrite it as a multiplication of a lambda, of a lambda, value here, which is an eigenvalue, scalar. So this is called an eigenmode of the system A, or the magnitude of the system A. And the same vector here, x, we want to identify the same vector. And if we identify or get the same vector x, right? So this will be called an eigenvector, which changes only in magnitude and not direction, okay? So this is the eigen decomposition. You want to, express mathematically this action of geometric action of the matrix A onto a particular vector X as a multiplication of a scalar onto the same vector. Okay, and these vectors X are very special because we call them eigenvectors, and the lambda, they are also special because they are assigned to these eigenvectors. So each eigenvector has an eigenvalue assigned to it. All right. So eigenvalues are sometimes thought of as the natural modes of a system A. We call them the natural modes. These are the eigenvectors. So for example, the eigenvalues of an oscillating system are its natural or resonant frequencies of its oscillations, and the eigenvectors correspond to their shapes. Okay, so this is for, in physics, for an oscillating system. So you can see the eigenvector decomposition or the eigen decomposition is everywhere. It's in physics, it's rooted in mathematics, but it is very powerful in machine learning, because we have seen in lecture 11 of the machine learning blinks that the eigen decomposition of the covariance matrix, of the data covariance matrix, if we have training samples, and from these training samples, we identify or define our covariance matrix, we derive it from the training set. So it is actually equivalent to a principal component analysis, or PCA. So when we do an eigen decomposition of our covariance matrix here, the sigma, we get what we call X. So the eigenvectors will be an orthogonal, a set of orthogonal vectors or directions of maximum data variance. Okay, so they maximize the data variance, and this is what we have seen. So if we have a data like this is a distribution. So we'll have PC1, which is the first eigenvector, and PC2, and they will be orthogonal. And the lambda is actually the variance in each direction. So the lambda quantifies the variance of the data. So this basically, lambda 1, and we have lambda 2. Okay, so that quantifies the variance of the data. And now, we will look at the adjacency matrix. So the same thing. So you can see that this eigen decomposition, as I mentioned, is very powerful. So when we apply it to graphs, so here we have an adjacency matrix of a graph with positive values. So in this case, we have positive values. So we're going to get what we call the principal eigenvector with the largest. So here are the principal eigenvectors with the largest eigenvalues. They give a topological measure of the centrality of each node. And, the largest eigenvalues here are right here. So the eigen value here tells us something about the centrality of the node, and we do this for each node. And this gives us what we call eigen vector centrality. And you guys can also go back to this lecture 2 of graph theory and watch that. So I go over this in detail, covering all the mathematical details and intuition behind this. So the key idea I want you to take out of this is that we can use the eigen decomposition of a graph adjacency matrix. Okay, so this is a graph. We do the eigen decomposition to get the eigenvalues, which will quantify the importance of nodes in the graph. So for example, this graph right here, it represents a brain connectivity graph. So here we have regions in the brain. Okay, so and it's of course brain regions. It's a symmetric matrix, and we decompose it into a set of the lambda times the eigenvectors. Okay, so this is the eigenvectors. So I'm gonna if I call this big X, so it's like big X, okay? And what happens here is that we're having all these eigenvalues because we're gonna take each value right here and multiply it by this vector. So it gives us exactly what we want. It gives us the X1 and lambda 1. And you can see that the values are ordered according by decreasing magnitude. So the highest ones are on top. And this tells us that this gives us the lambdas for each, node in the graph, it tells us, what are what is the topological centrality of all nodes in the graph. Okay, so these eigenvalues are very important. All right, so that was the spectra of the matrix, and this is just, a sneak peek. So spectral analysis of a graph, you can have a full course on that for weeks, covering so many methods, a lot of mathematical notations, and a lot of also rationales and principles that we can discover or derive from doing the spectral analysis of graphs. So next, we'll look at the organization pattern. So as I mentioned in the topology point, so number 4 here, we said there is what we call microtopology, mesotopology, and macrotopology. And if we plot the distribution of particular topological measures, we can imagine the structure of the graph. Okay, so we can eavesdrop on the structure and the connectivity of the graph. And this is an example here. So we can use different topological measures, or we can define graphs with particular organizational patterns or organizational properties. So for example, in this paper that was published in 2013 in PLOS 1, exploring the morphospace of communication efficiency in complex networks. So here, the x-axis denotes the efficiency of diffusing a signal along a graph, and this is the routing efficiency. So there's also another lecture where I covered in detail how we calculate these efficiencies. How do you calculate the diffusion efficiency of a graph and the routing efficiency of a graph in the graph theory course? But the key idea that I want to share here is that these graphs have different shapes. They have different, let me write them. So graphs have different shapes. They have different patterns, okay? They have different organizational topologies. And you can see here, for example, in terms of efficiency, the graphs that have the highest routing efficiency and the highest diffusion efficiency are the star-like graphs. So the star-like graphs means these graphs that happen to be along this front 2 here. So these are graphs where you have a central node and a bunch of peripheral nodes, or a central cluster and a bunch of peripheral nodes. So you have like, a sort of a star-like graph, like maybe a few like densely connected core here, a few densely connected nodes within a core, and a lot of peripheral nodes around, okay? So for another type we find in front 3, so in this front we find what we call the core structure node. So the core structure node, you have a core and you have like a sort of a bunch of peripheral nodes emanating from the core. So you have different topologies. Here you have a huge core and a few, kind of peripheral nodes. So this is what we call, the core structure also in a graph. Another structure is found in front 1. So this front, which has kind of low diffusion, it depends where you are on this front, okay? But you can see that graphs that are right here, they have low efficiency. So they have low efficiency, whether you calculate it via diffusion processes on graphs or routing processes on graphs. So these are 2 different ways of quantifying or measuring efficiency of information circulation, propagation through a graph. So you can see that these are actually the worst. They do not diffuse information very well. Why? Because they have these long paths. So you can see, for example, to get from a node in this cluster to a node in that cluster, you need to traverse all these nodes. So you need to spend a lot of energy. But for example, from here to get to any node to visit, any pair of nodes, you just need 2 hops, right? So you just need to pass through the center. So you need a short walk. So this structure is actually very efficient. The other structures right here, like this one, is the worst ever. Like, look, like just to get from one node here to there, you need to traverse all this kind of, long path of nodes. Okay, so these structures are not efficient in diffusing and conducting information or signal along them. So it's important to know your graph in terms of organization and patterns. It's important to visualize your graph to see how your graph looks like. Also, you can display the matrix to see if the matrix has some particular properties, such as a whole block that has a lot of connectivities, the rest are zero. So visualizing your matrix, plotting and also showing or displaying your graph can help if you have the resources. Of course, if you have billions of nodes, this becomes maybe a very challenging thing to do. Okay. So the last point here is efficiency and resilience. So as I mentioned earlier, so we covered different types of graphs and organizational patterns, topologies. So we can look at the matrix and identify and measure the efficiency and the resilience of this matrix to attacks. So in a matrix, you can attack a node, you can attack an edge. Okay, so if we do attack a node by randomly blocking it or randomly removing it or deleting it, what happens to the whole graph? So this tells us a lot in terms of what happens to the whole graph, what happens to the information circulation in the graph. So if you have an airport, for example, that is shut down, how would that affect flights between different cities or countries? All right. So basically, these two words are very important. If you guys are interested, you can watch also the full lectures 5 and 6. I cover them in detail. Like, for example, I go over the percolation, what we call a percolation threshold. So a percolation threshold is a value at which the graph breaks. So if you start, for example, removing edges here, so we want to know that what is the proportion, what is the ratio of edges that we need to remove for our graph to become fragmented and completely isolated, composed of isolated islands or fragments, okay? So this also, this threshold is important to study and examine the resilience of graphs. So also when you look at efficiency, you have two different concepts. You have global efficiency, you have also the local efficiency. So you can study the efficiency of a single node in a graph, but you can study also the efficiency of the whole graph itself. And here you can see that this graph topology is more efficient, okay, compared to this one. All right, as I explained earlier, how do we calculate efficiency? By checking the speed at which the information will go from one region to another, from one node to another node. So here it takes a long time, but if you want to go from this node to this node, you just need to go through this path and pass through what we call the core of the network, okay? So efficiency basically looks at how the topological properties of graphs constrain the way in which information flows through a graph. Also, which specific graph properties can be used to gain insight into information processing by graph units, which are the nodes and edges. So which kind of graph properties we can define or derive from this adjacency matrix to quantify or measure the information processing power and potential of this graph. Okay, so these are very deep and very important questions, and these will be revisited in deep graph neural networks and GNN models in different ways. But the field is still new, I would say, although it has been there for a few years. But there's a whole lot to do, and many of these concepts have not been integrated and investigated in much depth. Okay. So that was the adjacency matrix. So we diagnosed it, its efficiency, resilience, topological organization, its spectra. Also, how can we, raising it to the power of L can give us insights into the walks we need from one node to other nodes in the set of nodes that have that length of walks. And yeah, so that was a big overview. And next, we're going to look at the third section, the last section in this lecture, which is the learning task. So we'll cover that quickly, and I'm going to give you examples like just about the different tasks that we can learn using graphs. All right.